Module 21, Lecture B, MLP Training. By the end of this lecture, you will be able to configure MLP architecture, solvers, learning rates, and batch sizes, apply regularization, early stopping, warm starts, and incremental fitting, and diagnose scaling, convergence, and practical limitations of Scikit-Learn MLPs. Architecture regularization. Alpha regularization. Alpha regularization in a multilayer perceptron limits overly large connection weights, helping the model avoid memorizing noise in the training data. A smaller alpha lets the model fit more complex patterns, while a larger alpha pushes it towards simpler ones. This improves generalization by reducing predictions based on fragile or accidental details. Choosing the right alpha value helps a neural network balance underfitting and overfitting. If alpha is too high, the model may be too rigid and miss real patterns. If it is too low, the model may learn noise instead of useful signals. The best value depends on the dataset size, noise level, and model complexity, with larger networks and smaller datasets usually needing stronger regularization. Choose alpha regularization together with the model architecture and training setup. Larger neural networks often need stronger regularization, while smaller ones may need less. And proper feature scaling helps keep optimization stable. In Scikit-Learn multilayer perceptrons, start with a reasonable architecture, try several alpha values, and use validation results to find settings that give stable, reliable predictions. Python code, alpha regularization. Compare different alpha values in a small, multilayer perceptron to see how regularization affects performance. Alpha discourages overly large network weights, and validation accuracy reveals the trade-off between too little and too much regularization. We import key Python tools for a simple machine learning workflow: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for modeling. From Scikit-Learn, we use a moon-shaped synthetic dataset, split it into training and validation sets, standardize the features, and build a multi-layer perceptron classifier. A pipeline helps combine pre-processing and model training into one streamlined process. We create a synthetic two-dimensional crescent-shaped dataset using Scikit-Learn's MakeMoons function to test classification methods. The dataset has 600 samples, added noise to make the task harder, and a fixed random state for reproducible results. It produces input features along with target class labels. The code verifies that the features array has 600 rows and 2 columns, confirming the dataset has the expected number of samples and features. If the dimensions are wrong, it raises an error to stop the process. This validation helps catch data preparation problems before analysis or model training begins. We split the data into training and validation sets using Scikit-Learn's train test split function, with 35% reserved for validation. Stratifying by the target keeps the class balance consistent in both sets, and a fixed random state makes the split reproducible. This separation helps prevent data leakage, especially before applying scaling. We test several regularization strengths to see how they affect the model. Regularization helps reduce overfitting by discouraging overly large neural network weights. For each setting, we record the training and validation accuracy so we can compare performance as the regularization strength changes. We train the neural network several times using different regularization strengths. Each model is a multilayer perceptron with one hidden layer of 30 neurons, and regularization helps reduce overfitting by discouraging large weights. Training is allowed enough iterations to converge, and a fixed random state keeps the results reproducible. A pipeline is built to standardize the features before training a multi-layer perceptron classifier, helping the model work with normalized input data. The model is then trained on the training set, and its accuracy is measured on both the training and validation data. These scores are stored to compare how well the model learns the training patterns and generalizes to unseen data. The code reports the Scikit-Learn version, the alpha values tested, and the validation accuracy for each one. This summarizes how different regularization strengths affected performance on unseen data and helps identify the best alpha value. Create a plot canvas. Then graph training and validation accuracy against the alpha values using circular markers. Label each line clearly so the two curves can be compared. This shows how changing alpha affects both training and validation performance. The plot summarizes how MLP accuracy changes with alpha regularization strength. A logarithmic x-axis makes the wide range of alpha values easier to compare, while the y-axis shows accuracy. The title identifies the regularization trade-off, and the legend separates training accuracy from validation accuracy before the plot is displayed. This script shows how alpha regularization affects a small multilayer perceptron trained on a synthetic moons dataset. Alpha controls the penalty on large weights, so low values can overfit the training data, while high values can underfit and reduce both training and validation accuracy. By comparing accuracies across alpha values on a logarithmic scale, the plot highlights the bias variance trade-off and helps identify a suitable regularization strength for this model and dataset. Hidden layer design. Hidden layers in a multi-layer perceptron determine how well the model can learn useful patterns from input features. Simple tasks may need only one small hidden layer, while more complex tasks may require larger or multiple layers. The key is to match the model's complexity to the data, avoiding underfitting from too little capacity and overfitting from too much. When choosing hidden layers and units, aim for a balance between model power, stability, and generalization. A single hidden layer is often enough for many nonlinear patterns, especially with tabular data. Deeper networks can learn more complex patterns, but they usually need more data and careful tuning. In Scikit-Learn MLP models, it is best to start simple and add complexity only when needed. Designing hidden layers means balancing model capacity with training stability and efficiency. Wider or deeper networks can learn more complex patterns, but they may be harder to optimize and often need well-scaled data and suitable solver settings. In practice, choose an architecture by testing options on held-out data, checking for underfitting or overfitting, and considering how the model will be used. Python code. Hidden layer design. Compare different hidden layer sizes within the same multi-layer perceptron to see how width affects performance. Wider layers can increase the model's capacity, while validation accuracy helps identify the best trade-off for the architecture. This setup imports the main tools needed to build and evaluate a simple neural network classifier. NumPy supports numerical work, Matplotlib handles plotting, and Scikit-Learn provides machine learning utilities. The workflow creates a synthetic moon shapes dataset, splits it into training and test data, standardizes the features, and trains a multi-layer perceptron classifier using a pipeline so preprocessing and modeling are applied consistently. We create a small nonlinear classification dataset using the makeMoons function, which produces two interleaving half circles. The dataset includes 600 samples, with added noise to make the task more realistic and challenging. A fixed random state ensures the same data is generated each time for reproducible results. The code verifies that the features array has 600 rows and 2 columns, confirming the dataset was created with the expected number of samples and features. If the dimensions are wrong, it raises an error to flag the problem early. This helps prevent later issues during analysis or model training. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 30% reserved for testing. Stratification keeps the target variable's distribution consistent across both sets, and a fixed random state makes the split reproducible. We define several neural network architectures by specifying how many hidden layers they have and how many units are in each layer. Matching labels are created so the architectures can be identified during comparison. An empty collection is also prepared to store each model's accuracy after training and evaluation. The process tests several multi-layer perceptron architectures by changing the hidden layer configuration. For each one, the features are standardized, the classifier is trained with the Atom optimizer, and the model is fitted to the training data. Its accuracy is then measured on the test data and saved so that different architectures can be compared. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then compares several neural network architectures using held-out test data, printing each architecture's label and its accuracy rounded to 3 decimal places. This gives a concise summary of how the different model configurations performed. This plot compares test accuracy across different MLP hidden layer designs. A bar chart is created with each bar representing one hidden layer configuration and its corresponding accuracy, using clear axis labels and a descriptive title. The y-axis is limited to the most relevant accuracy range, from 0.7 to 1, making it easier to compare model performance. Finally, the Matplotlib show function displays the bar chart of test accuracies for each hidden layer configuration. This makes it easy to compare how different neural network architectures performed and assess how model capacity affected accuracy. This script compares how hidden layer size affects a multi-layer perceptron on a nonlinear synthetic classification task. After splitting and scaling the data correctly, it trains several networks with small, wider, and deeper hidden layers using the same optimizer settings. It then measures test accuracy and compares the results visually. The main takeaway is that larger or deeper networks often improve accuracy, but they also increase model complexity. Solver choices. Choosing a solver for a multi-layer perceptron in Scikit-Learn determines how the model learns its weights. The LBFGS solver is often effective for smaller datasets and simpler models because it uses information about the loss surface, but it can require too much memory on large datasets. Stochastic solvers update weights using batches of data, making them more flexible for larger datasets such as transactions or sensor readings. Stochastic gradient descent gives direct control over training, but it must be tuned carefully. Its behavior depends on choices such as learning rate, momentum, batch size, and feature scaling. A learning rate that is too large can make loss unstable, while one that is too small can slow learning. Smaller batches add useful noise, but can make training less stable, while larger batches give smoother updates with less randomness. The Atom solver is often a good choice for Scikit-Learn multi-layer perceptrons because it adapts learning for each parameter and usually needs less manual tuning than stochastic gradient descent. It works well for many medium to large datasets, especially when features are properly scaled and the network is reasonably designed. However, it can still fail to converge if scaling, layer size, learning rate, or training iterations are poorly chosen. The best solver depends on the dataset size, model complexity, computing resources, and how much tuning you can do. Python code, solver choices. Compare different MLP solvers using scaled data to see how the solver choice affects training. Focus on the resulting accuracy and the number of iterations needed to train. We import key Scikit-Learn tools for building a wine classification model. The wine dataset loader provides the data, while the train test split tool separates it into training and testing sets for evaluation. We also use a multi-layer perceptron classifier for the neural network model, a pipeline to combine processing and modeling steps. and a StandardScaler to normalize features for better neural network performance. We load Scikit-Learn's wine dataset, a ready-made classification dataset. It includes wine sample features as the input data and target labels that identify each wine type. These features and labels are used to train and evaluate machine learning models. Before training, the code verifies that the feature data and target labels have the same number of entries. This ensures every feature row has a matching label. If the counts differ, it raises an error to prevent problems during model training. The dataset is split into training and testing sets, so each solver can be compared fairly on the same data. Using Scikit-Learn's train-test-split function, 30% of the data is reserved for testing and 70% for training. Stratifying by the target keeps class proportions consistent, and setting the random state to 42 makes the split reproducible. To compare how solvers affect neural network training, the network architecture is kept the same while testing common optimization methods such as LBFGS, stochastic gradient descent, and ATOM. The results record each solver's accuracy and training iterations, making it easier to isolate how the choice of solver influences model performance. The process tests each solver by creating a new multilayer perceptron classifier for it. Each model uses one hidden layer with 12 neurons, trains for up to 800 iterations, and uses a fixed random state for reproducibility. The learning rate starts at 0.01 to control the optimization step size. A pipeline is built to standardize the input features before training a multilayer perceptron, helping the model converge more effectively. After fitting the pipeline on the training data, the model is tested on unseen data to measure accuracy. The solver's convergence iterations are also recorded, and the solver name, accuracy, and iteration count are saved for later comparison. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then keeps the neural network architecture fixed, using one hidden layer with 12 neurons, so any performance differences can be attributed to the solver. Finally, it prepares a results summary, showing each solver's test accuracy and number of training iterations. The code goes through the results for each model and prints a clean summary of its performance. For each solver, it shows the solver name, the test accuracy rounded to 3 decimal places, and the number of training iterations. The output is formatted so the solver names line up neatly. This script compares 3 solvers for training a multilayer perceptron on the wine dataset. It loads and normalizes the data, splits it into training and test sets, and trains the same neural network using LBFGS, stochastic gradient descent, and ATOM. For each solver, it reports test accuracy and the number of training iterations, showing how the solver choice affects both performance and convergence speed. Training controls. Learning rate control. Learning rate control determines how strongly a multilayer perceptron changes its weights during training. If the rate is too high, training can become unstable and overshoot good solutions. If it is too low, learning may be slow or stall. A well-chosen learning rate helps the model make steady, meaningful progress as it adapts to the data. In Scikit-Learn MLP Training, the learning rate controls how strongly the model updates during iterative optimization. A constant rate can work well when it is well matched to the task, while an adaptive rate starts faster and slows when progress stalls, helping with later fine-tuning. Together with regularization and early stopping, learning rate control helps the model learn useful patterns without overfitting. Choosing an effective learning rate depends on both the data and the training setup. If features are not properly scaled, some can dominate the weight updates, leading to slow or unstable learning. For an MLP, the learning rate should be considered alongside pre-processing, solver choice, and regularization. A good learning rate strategy helps training converge efficiently and improves performance on real-world data. Python code, learning rate control. When training a multilayer perceptron, the learning rate controls how quickly the model converges. Proper scaling helps keep neural network updates stable, while different learning rates can lead to faster or slower convergence. This setup imports the main tools needed to build and evaluate a simple machine learning model. NumPy supports numerical work, Matplotlib enables plotting, and Scikit-Learn provides the breast cancer dataset, data splitting, pre-processing, and modeling tools. The workflow uses a training and testing split, standardizes the features with a scaler, and applies a multilayer perceptron classifier through a pipeline. We load the built-in breast cancer classification dataset from Scikit-Learn, which includes both input features and target labels. The features and labels are separated so the data is ready for pre-processing and training a machine learning model. Before training, the code verifies that the feature data and target labels have the same number of entries. This confirms that every feature set has a matching label. If they do not match, it raises an error because the model cannot train correctly with misaligned data. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, while stratification preserves the original class balance in both subsets. A random state of 42 makes the split reproducible. We choose 3 learning rates to compare how training speed affects the neural network. We also set up storage for each rate's loss over time and its test accuracy, so we can later evaluate how quickly the model improves and which rate performs best. For each learning rate, a Scikit-Learn multilayer perceptron classifier is trained with one hidden layer of 20 neurons. It uses the atom optimizer, a small regularization term to reduce overfitting, and a maximum of 120 training iterations. A fixed random state ensures reproducible results, while verbose output is disabled to keep execution clean. The workflow builds a pipeline that standardizes the input features, then trains a multilayer perceptron classifier on the training data. After training, the model's loss curve is saved to show how learning progressed over iterations. Its accuracy on the test data is then recorded to measure how well it performs on unseen examples. The code reports the Scikit-Learn version to support reproducibility, then summarizes the results for each tested learning rate. For each rate, it shows the rounded test accuracy and final loss, making it easy to compare how learning rate choices affect model performance. Create a plotting canvas, then draw one training loss curve for each learning rate. Each curve is labeled by its learning rate, so the results can be compared clearly. This plot shows how different learning rates affect the loss over training iterations. The plot is set up to compare MLP training loss across different learning rates. Its title explains the comparison. The horizontal axis shows training iterations, and the vertical axis shows the loss value. A legend identifies which curve belongs to each learning rate, making the results easier to interpret. Finally, we use Matplotlib's show function to display the loss curves for each learning rate. These curves make it easier to compare how different rates affect training convergence, including the speed and stability of learning. This script compares how 3 learning rates affect neural network training on the breast cancer dataset. It trains the same one hidden layer model with the atom optimizer for each rate, then reports the final loss and test accuracy on unseen data. It also plots the loss curves to show how learning rate changes convergence speed and stability, with smaller rates often learning more slowly and larger rates potentially learning faster but less steadily. Batch size. Batch size controls how many training examples a model uses before updating its weights. In a multilayer perceptron, smaller batches update more often, which can make learning faster to respond, but less stable. Larger batches give a broader view of the data, producing smoother learning, but slower adaptation. Batch size is an important choice when training multilayer perceptrons because it affects both generalization and early stopping. Smaller batches add randomness that can reduce overfitting, but they may make validation results noisy. Larger batches give smoother validation curves, making early stopping easier to judge, but they may lose some helpful randomness and miss minority patterns if the data is not balanced. The goal is to choose a batch size that balances stability with useful variation. Batch size should be chosen based on the dataset, model complexity, available memory, and training stability. Large batches can be inefficient for small datasets because they behave too much like full dataset training, while very small batches on large datasets can make training slow and unstable. In Scikit-Learn multilayer perceptron models, batch size matters most with stochastic solvers because it controls how updates are made. Always compare training loss with validation performance, since faster loss reduction does not always mean better generalization. Python code. Batch size. When training a multilayer perceptron, batch size affects how often the model updates its weights. Smaller batches lead to more frequent updates, which can change validation accuracy compared with larger batches. We import the main tools needed to build and evaluate a neural network classifier. Matplotlib supports plotting, while Scikit-Learn provides the breast cancer dataset, a train and validation split, a multilayer perceptron classifier, and a pipeline to combine processing steps. We also use a StandardScaler to normalize the features, which helps neural networks train more effectively. We load Scikit-Learn's breast cancer dataset, a common example for classification tasks. The dataset is separated into input features, which contain the sample measurements, and target labels, which give the class outcome for each sample. This prepares the data for later processing and modeling. Before training, the code verifies that the feature data and target labels have the same number of rows. This check ensures every data point has a matching label. If the counts do not match, it raises an error so the issue can be fixed before modeling begins. We split the dataset into training and validation sets to check how well the model performs on unseen data. Using Scikit-Learn's train test split function, 25% of the data is reserved for validation. Stratification keeps the class distribution consistent, and a fixed random state makes the split reproducible. The training setup tests 3 batch sizes, 8, 32, and 128. After training, the validation accuracy for each batch size is stored, so the results can be compared. This helps show how batch size affects model performance. For each batch size being tested, a machine learning pipeline is built that first standardizes the features and then trains a multi-layer perceptron classifier with one hidden layer of 20 neurons. The model uses regularization, early stopping, a validation split, a fixed random state, and a maximum of 300 training iterations. After fitting the model on the training data, its accuracy on the validation set is recorded for comparison across batch sizes. The code reports the Scikit-Learn version, the batch size is tested, and the validation accuracy for each one, rounded to 3 decimal places. Together, these outputs document the training setup and make it easy to compare how different batch sizes affected model performance. This plot compares different batch sizes with their validation accuracy for an MLP model. It uses a simple line plot with circular markers, labels the axes for batch size and validation accuracy, and focuses the accuracy scale from 0.85 to 1.0. The result is a clear visual summary of how validation performance changes as batch size varies. This script tests how batch size affects the validation accuracy of a multi-layer perceptron on the breast cancer dataset. It trains the same model with batch sizes of 8, 32, and 128, using early stopping to reduce overfitting. It then reports the validation accuracies and plots them against batch size, making it easier to compare performance and see whether smaller, more frequent weight updates improve generalization. Early stopping. Early stopping helps prevent a neural network from overfitting by checking its performance on validation data during training. At first, the model improves on both training and unseen data. But later, it may begin memorizing noise in the training set. Training is stopped when validation performance no longer improves, keeping the model at its best generalizing state. In Scikit-Learn multilayer perceptron models, early stopping helps choose a training length that avoids both underfitting and overfitting. It monitors validation performance and stops when more training no longer improves generalization. For example, a churn model may first learn useful patterns such as complaints and contract length. But with too much training, it can start fitting quirks in the training data instead. Early stopping helps control overfitting and improve training efficiency, but it must be used carefully. Holding out validation data reduces the examples available for training, which matters especially with small datasets, and the validation set must reflect the real problem well. Its behavior also depends on choices like regularization, learning rate, and batch size, so it should support, not replace. Python code. Early stopping. This example shows how early stopping works when training a multi-layer perceptron. Validation scores are used to decide when further training is no longer improving performance, so the process stops automatically. We import the main tools needed to build and evaluate a neural network classifier. These include plotting support, Scikit-Learn's breast cancer dataset, tools for splitting data into training and testing sets, measuring accuracy, training a multi-layer perceptron classifier, and standardizing features so the model can learn more effectively. We load the breast cancer dataset from Scikit-Learn as a ready-made classification dataset. It includes input features and target labels, which identify each sample's class. Together, these provide the data needed to train and evaluate a machine learning model. Before training, check that the feature data has the same number of rows as the labels. Each feature row must match one label, so a mismatch should raise an error. This protects data integrity and helps prevent training failures. The dataset is split into training and testing sets using Scikit-Learn's train test split function, with 1/4 reserved for testing. Stratification keeps the class proportions the same in both sets for a fair evaluation, and a fixed random state makes the split reproducible across runs. A standard scaler is used to put features on a common scale by centering them and giving them unit variance. It is fit only on the training data, then applied to both the training and test data. Using the same scaling parameters keeps the data consistent and supports fair model evaluation. A multi-layer perceptron classifier is configured with one hidden layer of 20 neurons, using ReLU activation and the Atom optimizer to learn complex patterns efficiently. Regularization helps reduce overfitting, while a batch size of 32 and a small initial learning rate support stable training. Training can run for up to 200 iterations, but early stopping uses a validation split of 20% and stops if accuracy fails to improve for 8 rounds. A fixed random state ensures reproducible results, and detailed training logs are turned off. Train the neural network on the scaled training data so it can adjust its parameters and reduce prediction error. Then use the trained model to predict labels for the scaled test data. Comparing those predictions with the actual test labels gives the test accuracy, which measures how well the model performs on unseen data. The code reports the scikit-learn version for reproducibility, then shows how many training iterations the model actually completed, which may be fewer if early stopping occurred. It also prints the test accuracy rounded to 3 decimal places, giving a concise measure of performance on unseen data. This plot shows how validation accuracy changes across training iterations during MLP early stopping. It uses a clear figure with labeled axes, a descriptive title, and a light grid to make the trend easier to read. Displaying the graph helps assess whether validation performance improves, levels off, or declines during training. This script shows how early stopping can improve training for a multilayer perceptron on the breast cancer dataset. After splitting and scaling the data, the model trains while checking validation accuracy and stops if it fails to improve for 8 iterations. The script then reports how many iterations were used, gives the final test accuracy, and plots validation accuracy over time. The main idea is that early stopping helps reduce overfitting by ending training once further progress is unlikely. Practical MLP limits. Warm start allows a multilayer perceptron to continue training from its previously learned weights instead of starting over. This preserves the model's state, so later training can build on patterns already learned. It is useful when testing a short training run first, then extending training if validation results look promising. Without warm start, each run resets the model, making performance changes harder to interpret. Warm start can help evaluate whether a multilayer perceptron is still improving across training runs. If loss continues to fall, the first run may have stopped too soon. If it barely changes, the model may be stuck or affected by poor learning rate choices, feature scaling, or architecture. In Scikit-Learn, these settings matter because MLPs are especially sensitive to scaling and optimization, so more training alone may not fix the problem. Warm start can speed up training by continuing from previous model weights, but it is not a complete way to adapt a model to new data. If the data distribution changes, it may preserve outdated patterns or introduce bias, so improvements must be checked carefully. When using warm start with Scikit-Learn multilayer perceptrons, treat it mainly as a way to extend training, document its use, monitor convergence, and rely on validation and scaling checks to confirm real gains. Python code. Warm start. Warm start lets an MLP continue training from its existing weights, instead of starting over. Comparing repeated fits with and without warm start shows how this choice affects practical convergence, as reflected in the printed loss values. We import key Scikit-Learn tools for building a neural network classifier. These include the breast cancer dataset loader, a function to split data into training and testing sets, the multilayer perceptron classifier, a pipeline tool for combining processing steps, and a StandardScaler to normalize features. Scaling is especially important because neural networks usually perform better when input features have similar ranges. We load Scikit-Learn's breast cancer dataset, a small built-in classification dataset often used for demonstrations. The data is separated into features and target labels, so a machine learning model can learn from the inputs and be evaluated against the correct outcomes. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that each set of features has a matching target value. If they do not align, the code raises an error to prevent training on mismatched data, which could lead to incorrect learning and unreliable predictions. We split the dataset into training and testing sets so both models can be compared fairly on the same data. The Scikit-Learn train test split function separates the features and target, while stratification keeps the class balance consistent in both sets. 25% of the data is reserved for testing, and a fixed random state makes the split reproducible each time. We normalize the data with a standard scaler, so the multilayer perceptron can train more effectively. The scaler is fitted on the training data, making its values centered around 0 with a standard deviation of 1. The same fitted scaler is then used on the test data, ensuring both datasets use the same scale for reliable model performance. A neural network classifier is created with Scikit-Learn using one hidden layer of 12 neurons. It uses warm start, so the model keeps its learned weights between training runs and can continue improving from the previous fit. Training is limited to 80 iterations, uses the atom optimizer, and starts with a small learning rate of 0.001. A fixed random state helps make the results reproducible. A multilayer perceptron classifier is created with one hidden layer containing 12 neurons. It trains for up to 80 iterations using the atom optimizer and an initial learning rate of 0.001. Warm start is turned off, so training begins with fresh weights each time, and a random state of 42 makes the results reproducible. We create two empty lists to record loss values across training rounds, one for the warm start model and one for the restart model. Tracking these losses lets us compare how performance changes when training continues from existing weights versus starting over each time. A loop runs 3 training rounds to compare 2 models. The warm start model keeps learning from its previous state, while the restart model begins from scratch each time. After each round, both losses are rounded and saved, making it easier to compare how their training progress differs over repeated sessions. We evaluate both the warm start and restart models on the test data using the model scoring method, which compares predictions with the true labels. Each accuracy is rounded to 3 decimal places. This lets us compare continuing training from existing weights with starting fresh each time. The output first shows the Scikit-Learn version to support reproducibility. It then compares training losses for a warm start model and a restarted model, showing how each fits the data across training rounds. Finally, it reports test accuracy for both models to compare how well they perform on unseen data. This example shows how warm start affects training a neural network classifier in Scikit-Learn. Using scaled breast cancer data, it compares a model that keeps its learned weights across repeated training rounds with one that restarts each time. The warm start model typically shows steadily decreasing loss, suggesting continued learning, while the restarted model may not improve as consistently. The final test accuracy comparison illustrates how warm start can support better convergence and performance. Incremental fitting. Incremental fitting updates a model in small steps instead of retraining it from scratch. In Scikit-Learn MLP models, this can be done by repeatedly applying partial training to new batches of data. It is useful when data is too large for memory, arrives over time, or needs regular updates, helping neural networks stay current with less training cost. Incremental fitting with Scikit-Learn MLP models must be used carefully because each update depends on the current model and the next batch of data. Batch order and size can strongly influence results, with early data creating bias and later data potentially weakening older patterns. It is not a direct substitute for full training, so validation performance, class balance, and feature scaling should be monitored throughout. With incremental fitting, keep pre-processing consistent across every update, especially feature scaling, because neural networks can misread values if new data is transformed differently from the original training data. Convergence is also harder to judge when training happens in stages, so use a stable evaluation set and monitor metrics closely. If updates stop helping or performance declines, full retraining may be needed, particularly for Scikit-Learn MLP models in controlled, moderate-scale pipelines. Python code. Incremental fitting. This demonstration shows how to train a small multi-layer perceptron incrementally, updating the model after each mini batch. By tracking validation accuracy after every update, you can see how performance changes during training rather than only at the end. This helps reveal whether the model is improving steadily, stalling, or becoming unstable, which makes monitoring updates important in practice. We import key Python libraries for building and evaluating a simple machine learning classifier. NumPy supports numerical work, Matplotlib helps visualize results, and Scikit-Learn provides tools to create a synthetic classification dataset, split it into training and test sets, scale the features, train a multi-layer perceptron classifier, and measure prediction accuracy. We create a synthetic classification dataset with Scikit-Learn's make classification function for quick model training and testing. It contains 900 samples, 12 features, and 3 target classes, with 8 features carrying useful information and 2 redundant features derived from them. A fixed random state of 42 makes the dataset reproducible each time it is generated. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is reserved for testing, while the rest is used for training. Stratifying by the target keeps the class distribution consistent, and setting a random state makes the split reproducible. Create a StandardScaler to normalize features so they have a mean of 0 and a standard deviation of 1. Fit the scaler only on the training data to learn the needed statistics and avoid information leaking from the test set. Then use those same learned statistics to scale both the training and test features, keeping them on the same scale while preserving a fair model evaluation. Before incremental training begins, the code verifies that the number of training samples matches the number of labels. This confirms that every feature set has a corresponding label, which is required for supervised learning. If the counts do not match, it raises an error, so the data dimensions can be fixed before training continues. To make mini batches more representative, the training data is shuffled before batching. A fixed random seed ensures the shuffle can be reproduced, and the same random order is applied to both the scaled features and the targets. This mixes the samples so each mini batch better reflects the overall dataset, which can support more effective model training. This setup defines a small multi-layer perceptron for incremental training with one hidden layer of 20 neurons. It uses stochastic gradient descent, a modest learning rate, and light regularization to update weights gradually while reducing overfitting. A fixed random seed makes results reproducible, and limiting each training call to one iteration supports step-by-step updates with the partial fit method. We first identify the unique target classes so the model knows which categories it must predict. Then we choose a batch size of 75 for each incremental update and prepare a place to record accuracy after each batch, making it possible to track test performance over time. The training data is processed in mini batches of 75 examples at a time. For each batch, the model is updated incrementally using the batch features and targets, while being given the full set of possible classes. After each update, the model predicts the test labels and its accuracy is recorded. This tracks how performance changes as the model learns from each new batch. The code reports key training information to track model performance over time. It shows the Scikit-Learn version, the total number of mini-batch updates, the test accuracy after the first update, the best accuracy reached during training, and the final test accuracy. Together, these outputs summarize the model's progress, peak performance, and ending result. This plot shows how an MLP model's test accuracy changes after each incremental partial fit update. A new plotting area is created, the validation accuracies are drawn with circular markers, and the axes are labeled by update number and test accuracy. The accuracy scale is kept between 0 and 1, with a light grid added for readability, so the model's learning progress can be assessed visually. This script shows how a small multi-layer perceptron can learn incrementally from mini-batches while tracking test accuracy after each update. It creates a 3-class synthetic dataset, scales the training features, and trains the model with stochastic gradient descent in batches. After every batch update, it measures accuracy on the test set to show how performance changes during training. The output includes a plot of accuracy over time and a brief summary of the number of updates, plus the initial, best, and final accuracies. Scaling convergence. When training multi-layer perceptrons in Scikit-Learn, it is important to scale input features because these models are highly sensitive to differences in numerical range. Features on very different scales can distort gradient-based weight updates and make optimization unstable or slow. Standardizing the data puts features on comparable scales, helping the solver converge more reliably. If an MLP performs poorly, first check that scaling was applied consistently to the training, validation, and test data. Convergence means training has reached a point where more iterations no longer meaningfully improve performance. In Scikit-Learn multilayer perceptrons, warnings about iteration limits or unstable validation scores can signal convergence problems. These issues often come from poor scaling, but may also involve the learning rate, model complexity, batch size, or stopping settings. To diagnose them, check that preprocessing, solver choices, learning rate, stopping criteria, and model size work well together. Scikit-Learn's multi-layer perceptrons are useful for general neural network work, especially on tabular data, but they are not a substitute for deep learning frameworks built for large or complex models. As data size and feature count grow, training may become slow or unstable, so convergence should be checked during evaluation. A good MLP should have stable preprocessing, reasonable convergence, and a clear advantage over simpler models such as logistic regression or support vector machines. Python code, scaling convergence. This example highlights how scaling can affect the convergence of a multi-layer perceptron. By comparing identical models with and without scaling, it shows that the scaled model is expected to converge more smoothly. This setup imports the main tools needed to build and evaluate a simple classification model. NumPy supports numerical work, Matplotlib creates plots, and Scikit-Learn provides machine learning utilities. The workflow includes generating a synthetic classification dataset, splitting it into training and testing data, standardizing the features, and training a multi-layer perceptron classifier through a streamlined pipeline. We create a synthetic classification dataset with 900 samples and 8 features using Scikit-Learn's classification data generator. 5 features are informative, 1 is redundant, and a fixed random state ensures the results can be reproduced. This setup mimics data with features on different scales, which helps demonstrate how scaling affects model convergence. To mimic real-world data with features on different scales, 2 dataset columns are rescaled in opposite directions. One column is made much larger, while another is made much smaller. This creates mixed feature scales, helping show how scaling can affect model convergence. The code verifies that the dataset has 900 rows and 8 columns before analysis begins. If the shape is different, it raises an error to flag the problem early. This safeguard helps ensure the data is correctly structured and ready for later analysis or modeling. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, while stratification preserves the original class balance. A fixed random state makes the split reproducible across runs. The model settings define a multi-layer perceptron with one hidden layer containing 20 neurons. Training uses the Atom Optimizer with an initial learning rate of 0.01 and runs for up to 120 iterations. A fixed random seed ensures reproducible results, and detailed training logs are turned off. We create a multi-layer perceptron classifier using the earlier settings and train it directly on the raw feature values without applying scaling. During training, the model adjusts its weights and biases to reduce prediction error. This lets us evaluate how the classifier performs without feature scaling, which can influence training stability and convergence speed. The pipeline first standardizes the input features, then trains a multi-layer perceptron classifier. Scaling gives the features a mean of 0 and a standard deviation of 1, which helps the model learn from normalized data. This can make training smoother and improve convergence. We compare two models by measuring test accuracy for one trained on raw features and one trained on scaled features. This shows whether scaling improves performance. We then inspect the multi-layer perceptron inside the scaled pipeline, especially how many training iterations it needed, to understand how scaling affects convergence. The output reports the Scikit-Learn version for reproducibility, then compares model accuracy using raw and scaled features, rounded for readability. It also shows how many training iterations each model needed, helping reveal whether feature scaling improved convergence speed. Create a Matplotlib plot to compare training loss for two models, one trained on raw feature scales and one on standardized features. Plot both loss curves with clear labels, add a title, label the axes as training iteration and training loss, and include a legend. Displaying the plot lets you compare how feature scaling affects convergence. This script compares two multi-layer perceptron models trained on the same data, where the features have different scales. One model uses the raw features, while the other standardizes them before training. With the same network settings, the scaled model usually converges faster and more smoothly, often reaching similar or better test accuracy in fewer iterations. The printed results and loss curves show why feature scaling is important for training neural networks effectively. In this lecture, you learn to configure MLP architecture, solvers, learning rates, and batch sizes, apply regularization, early stopping, warm starts, and incremental fitting, and diagnose scaling, convergence, and practical limitations of Scikit-Learn MLPs. In the next module, Module 22, we will go over clustering foundations.
Thank you for your attention. See you all in the next lecture.